Right, so this is related work with a bunch of people, and Patrick and Oleg are here in the audience. Oh. Some of that. Right, so have you ever woken up in the middle of the night, drenched with sweat, and you had the realization suddenly that you were programming the same function over and over again, essentially, for different data types? Well, you've been missing out. you should consider looking at generic programming, or data type generic programming, as we call it, to distinguish it from other trends, shall we say. So if you're in the Haskell community and you want to do generic programming, you would go for a practical option, which is to go to Haskell and download a library for generic programming. So there are quite a few options there. So let's look at them chronologically. So first, you have in 2002 a library by James Cheney and Ralph Kinson, a nice little library which is really cool to learn generic programming. And well, then you have Scrappy Boilerplate, which now ships with GHC, so many people know it. In 2004, you have a library version of Poly. 2005, you have an extension of C. That's how I'm going to call it, an extension to support extensible generic functions. 2006 is really a good year for generic programming. Only 4 libraries at least released that year. Only at the Haskell workshop last year, Neil Mitchell released Uniplate. And, well, I think this list will continue to grow because at least our department is going to release some libraries. So, there are good news and bad news. So the good news is that we really have a lot of offer to do generic programming. And the bad news is that you have a lot of libraries for generic programming. So it's really unpractical to just go out there and try the libraries one by one to see which one is the one you're going to use for your project. So, I'm not including some other approaches to generic programming in this list. But okay, so this is one of the motivations why we just went out and started comparing libraries for generic programming. So we hope that using our comparison, you will be able to decide which of these ones to choose for your project. And then also, could it be that if you're advising one of your friends, so this friend is waking up in the middle of the night, if you're advising him to pick up generic programming, which one is the library you're going to suggest? Could it be that the overabundance of libraries is somehow impeding the adoption of generic programming? So maybe we thought if we compare it, and you have some insights that at least making like, hierarchy of libraries, like some subsume others, so you could be able to, let's say, suggest the most general one. Then another reason why we're looking only at libraries and not at more general approaches is that Haskell plus extensions is powerful enough to define generic programs which previously you have defined in, say, generic Haskell. Although you incur into some syntactic overhead, at least your toolchain becomes a bit simpler because you don't have to use preprocessors. So our contributions are as follows. We have this comparison suite that pits libraries against each other. So you can really see whether on some particular feature one library does better than another. So we have designed our library to evaluate, we have designed our suite to evaluate libraries on 26 features or properties. The idea is that some of these features can really be tested by code. That is, if you can test that a feature is present just by writing code that uses it. So it's some sort of code is evidence. Yeah, so we're proving that the library supports that feature by showing you the code. So you have this huge repository of functions that show that some features are supported by respective libraries. So you can also see this benchmark as some sort of cookbook. So if you're wondering how to implement X in some generic programming library, you can refer to it. Right, so how do you go about designing such a comparison? A crucial question is, what are the features that you're going to consider for your evaluation? And that, of course, depends on the generic programs that you're going to write. So what we did is to collect the generic programs and look at what things you are using there, and then collect the features that are being really used. So just to mention a few of these scenarios. So the typical scenarios are, for example, you define some data type and you ask GHC to derive the quality. So that's something that you can express with generic programming. So you can cover many of the derived type classes in the Haskell project. Then a common example of generic programming is serialization. And maybe even one more common use of generic programming is generic traversals. That is, you could, for example, traverse a syntax tree bottom up and do something specific on some nodes. For example, you could call it variables or some other stuff. Then you would like to be able to generalize over the type on which map works, not only that it works on lists, but on other data types. Well, and so on. So the features that appear in these scenarios are what we'll pick for our comparison criteria. And we, of course, look at other papers to see if there are some more interesting criteria that we had to look at. Some instances are extensibility. You want to define a generic function in one module and then extend it with another case in a separate module. Right. So the intuition for using our comparison is that you look at the evaluation of a library, and you should be able to tell if this library is going to be useful in your project. So for that, you have to look at what are the criteria that correspond to the scenario. So we hope that in this way it will save you work when deciding which library to use. Probably there are a few people in the audience who are not familiar with generic programming, so I'm going to give a really quick introduction, but don't expect this to be a full tutorial, so maybe we're going to gloss over some details. So the classical examples you have, right. So the idea is that you have well, a company data type, and it can be really any data type. For example, a huge syntax tree. The idea is that you have tons of types that you want to do an operation on something very specific. For instance, you want to collect the salary of the employees of a company. Now, classically, you would just write tons of boring boilerplate. So you just write functions that traverse values of these data types and don't do anything interesting. So the interesting case is when you get to the salaries, you return a singleton list, and then you just accumulate all the results that are floating bottom up. Now, generic programming would help you to avoid writing this boring boilerplate. And such boilerplate occurs in different scenarios. That's what you want to avoid to gain some productivity. So how do you do it in structured boilerplate? Well, you have this very handy traversal combinator called everything, which takes some and it's going to compute a result of type R. So you just have to tell it how to do it. You pass it an argument that for every node A is going to compute the result R, and then as you traverse the tree upwards, you're going to combine the results of neighboring children. So now you can write the collecting salaries function just by instantiating the function everything to the right arguments. For instance, the combination would be just a append function. And here we just say, whenever it's a salary node, you collect the salary, and otherwise you have the empty list. Yeah. So how does this work? Is there some magic in libraries that support generic programming? Well, the trick is that you have to represent the structure of data types. So how does SIP does it? So the structure boilerplate. Well, every data type that has generic programming enabled has a definition of the instance type class. So GFOL describes how constructors are applied to arguments, and everything is ultimately defined in terms of GFOL. So if this was too quick for you, the important thing to remember is that all approaches represent the structure of data types, and a generic function is defined once, and due to this structured representation, you can specialize into different data types. So that is where the advantage of generic programming comes from. So let's look at some examples of criteria. So what are the things that you would like to know about generic programming library? So one of the examples of criteria is universe size. So what are the data types on which a generic function can be applied? You can have very exotic data types, such as nested data types. So you use this to encode some invariant in a data structure. For instance, here what you have is that the perfect data type is being called with an argument that is growing. Yeah, so it's growing by means of the for function. So here what you have is a perfectly balanced binary tree. And, well, not all generic programming libraries can be applied to such data types, so that's something you may want to look at. But maybe in a more, something more useful is to be able to work with mutually recursive data types, especially if you're a compiler writer. You have a huge system of data types and they refer to each other. So if you have a library that cannot deal with this, it's basically useless for you. So that's an important question to ask about the library. And then what other kind of questions there are? So what are the generic functions that can be defined? So it's about expressiveness. For instance, you have first-class generic functions. Can you pass a generic function to another? So here I'm showing a combinator of the Scrappy boilerplate library. Yeah, so you can see this is higher order because of the rank 2 type here. I have removed, there are some context here, sorry for this. So there is some context that I omitted here, but basically the important information is that this is not parametric on A, so A is constrained here. And what this context is giving me is the structure information. So these are just examples, right? So another thing is that you will have to give a hook definition. So not treating. So you don't want to treat all data types structurally. You want to also look at the type names. This is the case with salary function, for instance. You want to do something specific on salary nodes. Then something very important also is abstraction over type constructors. So the generic map library is constructing over F, which is of kind star to star. This is important if, for example, you want to write mapping over binary trees that you have defined, so, or other data structures. So the last two set of criteria that I have shown, they are easy to test with code. You just write the data type definition, for example, for mutual recursive data types, and you try to apply a generic function for it. But there are some other things that you would like to know about the library that are not easy to test. For instance, ease of learning in use, or overhead of library use, which is, as a programmer, how much extra effort do you have to put when using library A instead of library B. I'm going to talk a little bit at the end of the talk about how we evaluate this. Right, so what I've given you now was a set of criteria, so the things on which you evaluate generic programming libraries. But now I'm going to give you a little example on how you use this information. Yeah, so I'm going to consider a very common scenario, that is using traversals. Probably that is the kind of programming that you do if you use Scrappy boilerplate or Uniplate. Yeah, so the examples are traversing a syntax tree, and you could, for example, thread state in a monad and accumulate variable names, etc. So what criteria do you need for this? Well, in this programming style, traversals are often encapsulated as functions. You don't want to write the same bottom-up traversal. You want to abstract over that so that your code is smaller. So a traversal can be parameterized by some action, for example, transformation. The transformation could be like specific to one data type. It could work on many data types, or even it could work in a generic way. So the most general case requires that the traversal are included as first-class generic functions. Then something very important here is that you should be able to give data type-specific behavior, so you need the whole definitions. And also, in domain-specific situations, you want to define your own traversals. So you would like that they're just as easy to define as Haskell functions. They're just one-liners, let's say. So what's intuition? Libraries that have good support are also to use in traversal scenarios. Yes, but these are the criteria you have to look at if you want to use a library for this scenario. Right, so the first two criteria are tested by code. Let's see an example. For instance, first-class generic functions. We'll try to write the function gmapq, and these are the types that we have in these two approaches. So Scrappy boilerplate, and this is type class based library, which is quite nice. So here the context can become more specific. So you know that the value which you are applying is an instance of data, which is describing the structure. In EMGM we have something similar. Yeah? And the deal gmapq is that if you're given a generic function, and for instance, the const node of a list, then this function is applied to the children of this constructor. So why is this function generic? Because the children may have different type, so they have to be instantiated to different types. So Scopy boilerplate has no problem with this criteria because generic functions are just Haskell functions. So that means that higher order generic functions are just rank n Haskell functions. So there's no problem. You check it on the good side. For EMGM, it is a bit more tricky. So I don't expect to understand you to understand this code unless you're an EMGM expert. But the summary of this is that there is in EMGM you can write higher order generic functions, but they are a bit tricky. So they are more difficult to write than other generic functions such as equality. So in our scoring, we have three categories. So you have those libraries that have good support for scoring. So in this criterion, these are the libraries that score well. And sufficient support are those libraries that fulfill this criterion, but they require more effort than programming other generic functions. And you have those libraries that do not support this criterion. So that is the scoring that we will find in most criterion evaluation. Now let's look at ad hoc definitions. We have seen this function already. So you apply salaries to data structure A and it collects all the salary nodes. The type for EMGM doesn't change much. You just have this additional context because of a different approach. So in Scopy boilerplate, the definition is very simple. We already saw it. So the support is good. In EMGM, it has good support as well because the generic function definition is given in instance declarations. All you have to do is have an instance declaration that corresponds to salaries. So the verdict is that for the two libraries I have shown now, so Scopy boilerplate and EMGM, they have good support for ad hoc cases. But this is not the case, for example, of LIGD and Spine. Why? Because if you want to extend, you have just time. You have to go back to the source of the library and then modify it, which is really undesirable. Right, so the last thing for this scenario is that you want to do little work when you define a generic function. For instance, if you want to define a specific traversal for GHC, you just write basically a Haskell function with special cases to handle different syntax trees in different ways. However, if you take an improvement over Scopy boilerplate, improvement in the sense of extensibility, to define a new combinator, you have to do additional work because it's not only defining a Haskell function, but actually you have to define a dictionary type, you have to define a type class, you have to give a sub-instance for that dictionary type, you have to define a proxy. So that means that if you are going to define, let's say, a module with 10 traversals, you have all this additional syntactic overhead. So you have to consider this in your choice for using this library. So you just take, so what we're going to do is, we're going to look at a lot of the libraries that have good scoring on these three criteria, and this is Scopy boilerplate. And Uniplate is an interesting exception, because traversals in Uniplate abstract over actions that occur only one time, so they don't need to be generic. Now, you could be a little bit more relaxed in this scenario. For example, you could say that you actually want to have extensibility. So you look at extensibility criteria, and you would not mind too much about the extra overhead that you have to do when defining a generic function. So I hope that by showing you this example, I give you an idea of how to use this evaluation table. So as you can see, there are quite a few criteria and libraries here. So I don't intend to go into detail here. I'm going to use the keyboard because it's not working well. Well, so just to give you a quick idea about the table. The table is split into three parts. You have universe size on top. So these are the data types in which you can apply the library, your generic functions. And the second part is about expressiveness. So for example, if you're interested in extensibility, that is, in defining a generic function in one module and extending it with additional cases in a different module, then the libraries that have the full circle are the ones that you're going to choose. So in this table, when you have basically the libraries that have the most black spots are the ones that are the best. Yeah, but still you have to look at scenario-specific information. Now, you have some other criteria here that are a bit more, let's say, subjective. For instance, ease of use, how are you going to test that? Ideally, you would make a controlled user study and then which users completed the generic programming task very expensive to carry out. So we did it in the following way. We looked at the implementations of libraries, and basically we checked what are the difficult features that a library uses. If a library uses too many difficult features, then we concluded that it was too difficult to use for a beginning user. So in this table, having many black dots doesn't mean necessarily that it is good, as opposed to the previous table. Yeah, so you may want to look at this also when you're deciding which library you want to use in your project. Right. Then we carried out preliminary performance tests. So they are preliminary because some of the libraries do not implement all the cases. For instance, Unicode, which is quite fast, you cannot write functions with multiple arguments, so you cannot test the quality. So I made a little ranking of let's say, which is the library that is fastest here, but I'm going to show it at the end. Right, so the results are that there is not one best generic programming library, because you have trade-offs. For instance, Scrappy Boilerplate performs quite well in the traversal scenario, but if you are to improve it with extensible generic functions, then you have this additional overhead to define combinators. And well, there are other trade-offs as well. So EMGM supports extensible generic functions, but the problem is that if you want to write a first-class generic function, then you really have to write a lot of code, so it's not an ideal situation. However, as I've shown in this little example, it is possible to identify the best libraries in some scenarios. So there are additional resources that you should look at. For instance, we have written a technical report which goes into more depth about what are the reasons behind our evaluation for a specific library. And you can find the second table which talks about implementation details. And at this URL you can find instructions on how to download the generic programming benchmark. So the conclusions are that using our comparison script, hopefully you should be able to decide which library to use in your project without having to invest in many resources. And maybe a surprise when doing this kind of work is that it is not straightforward to say that library X cannot perform task Y, because then, for instance, Klaus Reinke and Oleg Kiselev came forward and they say, what is how you can implement generic mapping Scrappy Boilerplate, which was quite unexpected for us. And, well, we would really like more detailed performance measurements, because you can see that it's really worse than others, so it would be interesting to see what are optimization techniques that we can use. So this is what I wanted to talk about, so thank you for your attention.
So you talk about ad hoc data type definitions.
That's right.
That some libraries support and others don't. But a more detailed comparison would also involve how they interact with the type classes that already are in Haskell. So can you say a bit more about that? Have you considered that in the paper? Or?
No, so what we're talking about, I guess, is that so you have existing type classes in your program, right? And then you want to define a generic function.
Yeah, so the ad hoc behavior would be introduced by the user making an instance of the type class rather than annotating the function, because that's sort of the way you do it in type class.
Yeah, it sort of depends on different approaches. Yeah, so like for example, EMGM doesn't declare functions in type class in the way that you would usually expect. Yeah, for instance, for equality, you would expect that there's a type class equality on A's, and there's a method A to boot. And for instance, EMGM does it slightly differently. So they would look different than your handwritten instances in your program. Now, if you stick to the view of EMGM as the view of EMGM of generic functions, then there is no problem on adding your own instances to the generic function. Yeah, you can, like for that particular library, you can even add them in different modules, so it's quite handy if you are going to release this as a library that you could extend that functionality.
Okay, so that's exactly what you mean. Did you also have a black dot for that, or?
Sorry?
Did you also have a black dot for that property? Or?
Yes. So I sort of went very quickly through the table because it's very detailed information, and I'm afraid I probably cannot read it right. So this is a whole definition for data types.
But I was talking about the specific type class way, but anyway, we can take that one.
Yeah, sure, yeah. So, more questions?
Will you keep this up to date as an ongoing area?
So far I have been keeping it up to date, but it's really a lot of work, so I have to grab all my things.
Let everybody else keep it up to date.
Sorry?
Put it on the wiki, let everybody else keep it up to date.
Yeah. Yes?
I remember you were talking about whether these features can be standardized kind of comments then.
Yeah, it was sort of like an hypothetical, optimistic situation in which you could find out that, oh, actually, all these generic programming libraries, they look like each other, so you could maybe generalize it in this design. But I guess that's open work. You really have to look at the inner details of libraries to do that. But if you add to one library, then you lose from another.
So that means there isn't yet any converging.
I don't think there will be any convergence, or probably there will be convergence on specific scenarios. It becomes sort of obvious if you look at particular scenario that some libraries are just bad to do that. Yeah. So at least in that perspective, can happen.
In practice, did you find that most of the generic programming libraries followed similar paradigms, or were there any examples that were just radically different how you would solve the problem with a different
I would
library?
rather say the second, but it depends on the function. Yeah, so like you could look at how equality is defined. Yeah, so equality and sorry for that, I don't know how to use this. Yeah, so equality in LIGD is just defined like a normal Haskell function. You do pattern matching on a type representation, you do pattern matching on left argument, right argument, and then you can decide whether they're equal or not. Like if it sums, if it's left choice, right choice, it's false. Now, the structured boilerplate is not quite like that. There's quite some trickery going on to try, so you partially apply some functions to the constructors of the first argument, wrap them in a list, and then you unwrap them while you're traversing the second argument. So it's, I would call that radically different than the LIGD solution.
Any more questions? Let's